on. Hi everyone, we can start the next session. General Talk 1-3. And our chair is Gervasio Osvaldo. And he is here with me.
Hi. Thanks for attending this session. We can start with the paper presented, I hope, by Raffaele D'Ambrosio. And the title is Optimal Theta Methods for mean square
Yeah.
dissipated stochastic differential equations.
Yes. Thank you for this introduction. Just to remember that this paper is presented by me, Stefano Di Gioacchino, not by Raffaele D'Ambrosio, my supervisor of my PhD. Yeah, thank you. First of all, I would share my screen.
Yes.
Okay. Can you see my screen?
Yeah.
Yeah. Okay. I start. I would like to thank the organizer for this opportunity. Today, I would like to present you some results about nonlinear stability analysis for numerical methods in the stochastic differential equation setting. Just to record that this is a joint work with Raffaele D'Ambrosio at the University of L'Aquila. First of all, we will talk on stochastic differential equations of Ito type, assuming the following formulation. In this talk, F is the drift of the stochastic differential problem, G is the diffusion function, Wt is standard Brownian motion, M with dimension M. G is a matrix valued function of dimension D times M. F is a vector. For this problem, we assume the following assumptions. We assume that the drift and diffusion are C1 function. We assume that the drift is one-sided Lipschitz. In other words, the function f satisfies the one-sided Lipschitz condition with constant mu. Moreover, we assume that the function g is a global Lipschitz. There exists a constant L such that it solves the point 3i. As we mentioned in the title, we will talk about dissipative stochastic differential equations, in the sense that there is in the literature a theorem of Eigen-Claude and Clauden that represents our starting point of our analysis. Assume the condition I 3i, then choose solution x and y of an Ito stochastic differential equations with finite initial value in the mean square sense, satisfy the following exponential inequality, where alpha is 2 mu plus L. We will talk about dissipative stochastic differential equation if this alpha is negative, because if this alpha is negative, we have a decay of any deviation of any two solution in the mean square sense with respect to the initial value. At time 0 we have the value, expected value of x0 minus y0 at to the square. If alpha is negative at time t, this value is decaying in time, provided by alpha less than 0. These concepts are well developed in an important paper of Eigen and Clauden, numerical methods for nonlinear stochastic differential equation with jumps, and represent, as said before, our starting point. Then we have in the following setting, we have stochastic differential equations satisfying a certain property of interest P. This property is the dissipation in time of the mean square deviation of any two solution. Then we have to analyze if this property is retained along numerical solutions provided by theta Maruyama methods and theta Milstein methods that are the following that you can appreciate in this slide. In particular, the first is the so-called theta Maruyama method. Theta is a constant in 0, 1. For theta equal 1, we have the implicit Euler scheme for stochastic differential equations. For theta equal 0, we recast the Euler-Maruyama scheme, explicit Euler, for stochastic differential equation. For theta equal 1 half, we have, for example, the stochastic trapezoidal rule. Then we are interested in analyzing whether the dissipative in time in a mean square sense is visible also along numerical flow. For the case of theta Maruyama, we have proven the following result. Under assumption I3i, any two theta Maruyama numerical solution xn and yn satisfy the following inequality with nu, an exponent that is in general function of theta and delta t. Clearly, if nu is less than 0, any deviation between two numerical solutions of the problem satisfy dissipative property in a mean square sense. For any fixed value of theta, we have also proven that the numerical exponent nu differs from the x at 1 alpha by power of big O of delta t. In other words, if we take a step size smaller and smaller, the numerical exponent nu behaves close to the x at 1 alpha. An analogous result can be proven also for theta Milstein. The exponent really is different, is denoted by epsilon, or also in this setting, epsilon goes to alpha as power of big O of delta t. Then, for a nonlinear stochastic differential equation satisfying assumption I3i, is completely meaningful speaking about mean square conductivity region. A theta method is said to generate a mean square conductivity numerical solution in a region R, subset of R+, if for any fixed theta, the exponent function of theta and delta t, in the case of theta Maruyama is nu, or in the theta Milstein is epsilon, is less than 0. A stochastic theta method is said unconditionally mean square contractive if for a given theta R coincides with R+. In other words, if for every choice of the step size, the numerical solution shares the same dissipative behaviors of the exact problem. For theta Maruyama methods, the mean square conductivity holds true if and only if the coefficient beta is less than 0, 1, where beta is this constant defined here. And, for example, and in this case, R is R+ if theta equal 1. We are saying that the theta Maruyama method with theta equal 1, the implicit Euler-Maruyama scheme, is unconditionally mean square contractive. It is the only one, because for every values of theta less than 1, the mean square conductivity region is bounded above by this constant. Moreover, the value of theta is the optimal choice of theta in terms of mean square stability interval. In other words, it is possible to prove, and we have done it, that for theta equal 1 represent the choice maximizing the length of intervals of linear stability and non-linear stability. Theta equal 1 is the best choice we can do in terms of stability, numerical stability. For theta Milstein, we lost the unconditional conductivity also for the case theta equal 1, and also for this setting, the value of theta equal 1 represent the optimal choice of theta in terms of mean square stability interval. To conclude, we can just perform an example. We consider a stochastic Gis-Boolean equation where f is this function here, g is the identity function. In this case, the function of the type minus mu x plus beta x cube is one-sided ellipsis with constant mu. In this case, mu is minus 4. L equal 1. So alpha is equal to minus 7. Then this problem is mean square dissipative. Then we have applied the stochastic trapezoidal methods with the Euler-Maruyama method with theta equal 1 half. The region is the one you can see in this slide. This experiment reveals that if the step size became smaller and smaller, we recast a similar and very close behavior of the exact problem. As the step size goes higher, we lost an exponential decay. In conclusion, we have analyzed a structural preservation problem in the stochastic differential equation setting. We have avoided the construction of new schemes, analyzing the well-known schemes and studying the conditions under which these schemes are able to preserve a property of interest. In this case, mean square dissipation of the solution. We have proven that this property is translated along the numerical flow on restriction of the step size to use in the simulation. We have extended this analysis to other types of methods, such as the stochastic or Geputta method, for example, and in future it is possible to develop an analysis for other types of operators. This is a complete list of reference for this talk. I would like to thank you for your kind attention.
Well, thank you. Thank you so much for your presentation. Are there questions?
Yes, I have a question.
Please.
Sure.
Stefano, this analysis can be conducted for other types of noise?
Oh, yes, this is a good point. As said at the beginning, this property here,
yeah,
is has been proven in this paper, but I can include it for jumps, because also in the jumps case, in the stochastic differential equation driven by, for example, Poisson process, we have a dissipative property. So it is possible to perform this analysis also in this case, but this is an idea that we can certainly develop in future. Thanks for this.
Thank you. Thank you. Thank you.
Thank you. Thank you for the response. Well, I think we can pass to the second paper.
Thank you.
Thank you for your kind presentation. Which is the presenter?
Dai, Giuseppe Giordano.
Okay.
Perfect. So Giuseppe Giordano will present the paper Continuous Extension of Euler-Maruyama Method for Stochastic Differential Equations.
Yeah. Now I share my screen. Okay. Can you see my slides?
Yes.
Perfect. Okay. So I am Giuseppe Giordano, a PhD student from University of Salerno, and today I present a talk entitled Continuous Extension of Euler-Maruyama Methods for Stochastic Differential Equation. First of all, I would like to mention that this is a joint work with Professor Diana Conte and Professor Beatrice Paternoster from University of Salerno, and Professor Raffaele D'Ambrosio from University of L'Aquila. I start with an introduction of our problem. So a generic stochastic differential equation is described by this equation 1, in which, as can you see from this equation has two parts. The first, the drift of the equation, belongs to an ordinary differential equation, so a deterministic one. And the second part of this equation is the diffusion part. In particular, G is called the diffusion function of the equation, together with this differential term, dW, where W is an m-dimensional linear, a multidimensional linear process. And it is important to note that the solution of a stochastic differential equation is a random variable for each time step t. But the integral formulation of this equation is given by this second equation, in which this first integral is a deterministic one, so a Riemann integral, for instance, while the second one is a stochastic integral. And in this work, we refer it to Ito integrals, defined as a limit of this quadrature formula. And in particular, it contains the diffusion function G evaluates in some internal points, x on tj, times these differences, the so-called linear increments. And this formulation, the integral formulation, is much more interesting because we know how to simulate these differences, these linear increments, because they are the square root of h, where h represents the step size of our uniform grid, times a standard normal variable, so a normal variable with mean 0 and variance 1. Let us consider now the Euler-Maruyama methods. In particular, the Euler-Maruyama method is a prototype of the simplest numerical method to solve a stochastic differential equation. And xk in this equation third is an approximation of the stochastic process of the solution, so of the stochastic differential equation, in this point tk. Tk is one of the points of our uniform grid. And the aim of this work is to develop a continuous extension of this method, of the Euler-Maruyama method, based on the well-known idea of deterministic numerical collocation. And in particular, a numerical collocation for deterministic problems is a technique to develop dense output methods. And in other terms, the provided approximant, the so-called collocation function, is constructed as a linear combination of selected basis function spanning a finite dimensional function space. And usually these functions are algebraic polynomials. And the collocation function is required to exactly satisfy the given equation in a select set point of the integrational interval, denoted as collocation points. And in order to obtain a continuous extension of Euler-Maruyama method, let us consider the following answers, the following hypotheses. So, in a sufficiently small interval of length h, the solution of the given stochastic differential equation can be approximated by this linear function, where L1, L2 are the classical Lagrangian polynomials. Capital U1 and capital U2 are the value of this function Un in this point T and I described as follows, where C1 and C2 are two parameters with C1 lower than C2 and between from 0 to 1. Correspondingly, the numerical scheme is described by this equation 5, where Fn represents the lag term of the equation, contains all the past history of the dynamics up to the grid point n. And phi I and phi 2 are the incremental term described by this equation. But it is important to note that this scheme requires the solution of a system of two nonlinear equations in the unknown function capital U1 and capital U2. But if we set C2 equal to 1, the scheme can be simplified because Phi2 is a sum of these two integrals from Tn to Tn plus 1. And so capital U2, that is a sum of Fn plus Phi2, so we have an integral. F1 contains an integral from 0 to Tn, and Phi2 contains the integral from Tn to Tn plus 1. So the capital U2 is equal to the lag term at the next point. So it is equal to Fn plus 1. And so you can see that Fn is equal to Xn. And by mixing these three information, we observe that the approximation of the solution in the next point, so Xn plus 1, is equal to capital U2n. And so the scheme can be simplified because we can calculate more simple the approximation of the solution Xn plus 1. But this method involves the calculation of this integral because phi I and phi 2 contains these two integral. So this is not a fully discretized method, and in order to get it, we approximate these two integrals by a quadrature formula. For example, in this work, we use a rectangular formula, a rectangular quadrature formula, in order to obtain a discretized numerical method. And automatically, the continuous approximant of the stochastic differential equation in the interval Tn plus 1 is given by this equation 9. Well, we note that this scheme 8 represents a family of numerical methods because for any choice of parameter C1, we obtain a numerical method. And in particular, if C1 is equal to 0, the methods assume the following form. And so, since Xn plus 1 is equal to the second variable capital U2, we see that Xn plus 1 is equal to this expression described by this equation 10. And this is so the Euler-Maruyama method. And automatically, by imposing the equation 9 C1 equal to 0, we obtain a continuous approximant, a continuous extension of Euler-Maruyama methods. And it is important to observe that the continuous extension can be used because we know not only the solution in the point of the point of a uniform grid, but in all entire integration interval of the given equation. And so, at a numerical point of view, we observe that the methods, for example, by imposing C1 equal to 1 over 4, exhibit and apply this method on these three problems. We note that these methods exhibit the same weak order of convergency equal to 1, such as that of the Euler-Maruyama method. So these methods, all these methods of this family exhibit the same order of convergency of the Euler-Maruyama method. And to conclude, our work in progress is to implement a variable step size algorithm And in particular, we have done these local, and the first step, the first building block to implement a variable step size algorithm is to implement a local error estimation. And in particular, in this procedure, by using the continuous extension described above, we obtain that as we see that from this figure, we see that as the step size h decrease, the local error estimate is closer and closer to the local error. So you can see that if h is decreases, the gap between the local error and its estimation in red is tends to 0. And so the next step is use this local error estimation, the local error estimation, and the continuous time extension to obtain a variable step size algorithm. This is useful when you want to numerical approximation stiff stochastic differential equation. And these are some references which we found more details of this work, and thanks for your attention.
Thank you very much for your clear presentation and for respecting the time. Are there any questions, thoughts?
I will take a question, sorry.
Please.
Yeah.
Giuseppe, thanks for this talk. My sort of curiosity is it possible to extend this analysis in the case of a bigger number of parameters than 2?
So I think that you mean that if we have some collocation parameter, some parameter of this method, so it is okay.
Yeah, sure.
Yes, it is possible. So we have already tried to extend the procedure in this multidimensional case, but we have observed that the weak order of convergence remains unchanged. And so this would not make sense because the system of these nonlinear equations that we have a necessity to solve is more expensive. So this is not make sense. So for this reason, we have just 2 collocation parameters. So it is the minimum number to obtain the methods.
Okay. Yeah. Thank you.
Thank you for your question.
Thank you. Are there other questions? Okay. So we thank again Giuseppe for the presentation, and the floor now is for Oleg Smoky, who will present the mirror reflection principle and probabilistic invariance in the theory of multiple photon scattering. So we change. Is not present, Oleg? No. We cannot hear you.
I see the screen. So now, not.
Mr. Smoky, can you hear us?
Okay. Okay, please.
But we cannot hear you.
ladies and gentlemen, Mr. Chairman, colleagues.
Mr. Smatki, you are really low.
Can you increase the volume, please? Because we hear very, very bad.
Sorry. Sorry, one moment.
Yeah, yeah.
So,
Or maybe you can just get closer to the microphone.
just a moment, just a moment.
Okay, okay.
Now it's better. Yes, if you can approach the microphone
Microphone.
to stay closer to the microphone, so we can hear. So proceed, please.
So, doesn't work.
Share again your screen. Now we are not able to see the screen.
Mr. Smatki? Are you having technical problems?
It is correct. No?
No, we cannot see the screen. Sorry. Okay, good, good. Proceed.
Good.
Okay.
Sorry, ladies and gentlemen, for my delay. So, ladies and gentlemen, Mr. Chairman, colleagues, let me to introduce my paper titled The Mirror Reflection Principle and Probabilistic Invariant in the Theory of Multi-Photon Scattering. In the framework of the statistical interpretation on multi-photon scattering as stationary Markov processes. This was given the well-known works by Sobolev and Lena. In paper has formulated the principle of mirror spatial angular symmetry for total probability of photon exiting from homogeneous slab of finite optical thickness, based on the principle of linear second kind third-horn integral equation have been obtained, as well as a linear singular integral equation for new object of the classical radius transfer theory, namely probabilistic invariance in the case of the arbitrary distribution and power of the primary energy sources on the medium. Besides, a unified probabilistic function for photon exiting from homogeneous lab was constructed. Given the analysis connection between probabilistic and photometrical invariance, it has been shown that the calculations by standard computational method, such as discrete diffusion technique or method of successive approximation, lead to substantial saving of computer resources and provide a more convenient form for representation of theoretical data and results of numerical modeling of radiative fields in the atmosphere in the visible spectral range. Let me to represent my topics of my report: basic probabilistic function and its main properties, probability invariance of theory of photon scattering, the principle of spatial angular mirror symmetry of total probability of photon exiting from homogeneous web, symmetrization of my integral.
Please stay closer to the microphone because we have very
linear singular integral equation for probability invariance of a homogeneous slab of finite optical thickness. At last, a unified probability function for photon exiting for slab. This slide shows that this representation of basic notation of probabilistic treatment of radiative transfer theory is namely, it is you select this arbitrary optical level as tau, and this function, it is determine the probability of current events where absorbed photon at mentioned optical thickness exit after multiple photon scattering from given slab across upper optical level of this slab. Next slide shows this introduction on the theory probability invariance in the theory of multiple photon scattering. Normally, if you separate it instead one optical level, we can introduce two mirror symmetrical level, and this one, and symmetrical level, and this one. This mirror vision direction, and afterward you can образовать this following probability value. If you make this summing and this value in mirror symmetry level, in symmetrical direction in this level. In this context, in this probability function, you can consider as a function that determines this probability properties of mirror photon, and this mirror symmetry level in symmetry mirror propagation of photon. And mathematical technology formalizing in this relation, in this value for mirror photon, and this one, and this the same value on this another angle, and this value for on this another structure, which determines this difference between probability value this mirror symmetry level. It's very important emphasize that is information about this probability invariant. This one and this one allow this determining this initial probability function. There's another probability function. This characterization in this photon that emission from no absorption, no emission photon that after multiple light scattering exit from upper layer on the given slab. It's very important emphasize also the basic properties of this probability invariant, namely in this equal value after translation in this optical, this initial optical is mirror symmetrical level. In this angle of vision, it is mirror symmetrical angle. And this very important that mention properties allow to significantly improve on this numerical scheme of calculation of probability value of radiative transfer theory. Classities you can show our form and this probabilistic invariant if you introduce this new principle of spatial angle mirror symmetry of total probability of photon exiting homogeneous lab. In this problem, is initial you can consider this ordinary processes of multiple light scattering photons in homogeneous lab, and this from this initial level is symmetrical level. And if you consider this mirror reflection picture relatively in this initial picture, you can receive in this processes for multiple light scattering photon in symmetrical level, mirror symmetrical relative in this mirror symmetrical level and this. If you joint in this probability invariant, you can receive in this mentioned above probability invariant. It's formally in this formational expression this relation.
Professor Smoky, please go to the conclusion. We are late.
If you using this consideration, you can join this processes of initial in mirror picture. On this, for this, it is necessary to join this primary initial primary source in the slab for initial mirror source energetical source. Thus, for formulating and subsequently solving basic symmetrization problems on the theory of multiple isotropic photon scattering, it is necessary first to carry out the following combined types of spatial angular symmetrization. Firstly, symmetrization rational optical level that is near position or relative to middle of the given homogeneous slab. Second, symmetrization of direction of static photon propagation. And last, mirror symmetrization of the location of primary electrostatic energy source relative to middle of given homogeneous slab. Further, you can use in this results received by Sobolev and Minin and establish a connection between probabilistic invariant according to following differential equation. Solution of this differential equation have in simple form. For this kind of probabilistic invariant, the second kind of probabilistic invariant. On the basis of previous results, you can receive in this new linear second kind trivial integral equation for probabilistic invariant in a homogeneous slab of finite optical thickness. This linear integral equation has its following for another probabilistic invariant in this integral equation trivial second kind has analogical form. If you use connection between introduced probabilistic invariant of radiative transfer theory is appropriate photometrical invariant, this source function of processes multiply light scattering, intensity of radiation.
Professor Smoky, can you please go to the conclusions?
You can receive following making use of following form on this photometrical invariant introduced by our radiative transfer theory. You can use the basic properties of invariance of these photometrical values, namely for translation on this symmetrical level and symmetrical direction of vision, you can receive as equal values for this thousand function and intensity. So consequently, making use of this results obtained by Malekin and Sobolev in classical radiative transfer theory in previous connection, it is photometrical in probability. You can construct this new linear singular integral equation for probability invariance of a homogeneous slab of finite optical thickness. This function and this function represented as into harmonic of well-known function of classical radiative transfer theory being by Stochastic and Sobolev, for example. This analogous linear single equation for probabilistic invariant homogeneous and finite optical thickness.
Professor Smoky, please go to the conclusion, please. We are running out of the time, please.
Sorry, I 2 minutes, okay? 2 minutes.
2 minutes.
At last,
Okay.
on the base received result, you can introduce unified probabilistic function for photon-exciting homogeneous map on finite optical thickness. This function is joint to this probability value in optical, symmetrical optical levels and mirror symmetrical vision direction. And this for probability value. At last, let me formulate this one results. Introduce in radiative transfer theory basic conception of probability invariance unified probability function for photon exciting homogeneous type of arbitrary optical thickness obtained linear second kind for dual integral equation in linear single integral equation for probability invariance, and the homogeneous lap of arbitrary optical thickness. At last, by using this probability invariance, it is possible to substantially decrease the effective domain of spatial angular variables needed for analytical and numerical modeling, and to reduce time for computation of probability invariance in the case of arbitrary distribution of power of primary energy source in a given homogeneous type of arbitrary optical thickness. Thank you so much for your attention.
Okay, thank you. We are running out of time, so we go straight to the next presentation made by Mariana Rocamonde Mendoza. Ensemble Feature Selection compares to meta-analysis for breast cancer biomarker identification from microarray data. Please, Mariana.
Hi, can you hear me?
Yeah,
Yes.
very well.
Okay, I'll just share my screen just a minute. So, can you see my screen?
Yeah.
Yes.
Okay.
Thank you for attending the conference. I guess it's quite early in your country.
Yeah, so it's around, it's not 7:22, but okay.
Okay, thank you.
So, thank you very much. So, my name is Mariana Mendoza. I'm a professor at Federal University of Rio Grande do Sul and Clinical Hospital of Porto Alegre, and I'll be presenting the work developed by my student Bernardo Trevisan about homogeneous ensemble feature selection for breast cancer biomarkers identification from microarray data. So this is our agenda. I'll introduce our motivation and goals and some related works. I'll explain our methodology and experiments, and then I'll summarize our findings. So cancer is among the main cause of death, and breast cancer specifically is the most common type of cancer. So the understanding of genomics of cancer may help improve diagnosis and treatment, which is one of the main goals to improve disease outcome. And biomarkers in special, they can be investigated as indicators of the presence or severity of the disease. So there is an increasing volume of omics data, such as transcriptome, but its analysis is very, very challenging. So new analytical tools are needed to leverage omics data for new biomarkers, and machine learning is a promising direction. So the goals of our work was to explore an ensemble feature selection strategy to identify candidate biomarkers for breast cancer from a compendium of microarray datasets. We are analyzing result stability, classifiers performance to distinguish among tumor and non-tumor samples, and compare with meta-analysis, which is the state-of-the-art method in the literature. So ensemble feature selection aims at combining diverse solutions obtained either from data perturbations such as data samples or distinct feature selection algorithms to improve overall results, including stability. Here we are dealing with homogeneous ensemble feature selection. The use of ensemble feature selection with high-dimensional data such as transcriptome is not new. Several works show that we can improve predictive performance over individual feature selectors by combining the results, but few works have looked at stability, which is very crucial for biomarkers. Also, previous homogeneous ensemble feature selection, they use sampling strategies from the same dataset, where here we are aiming at combining multiple microarray datasets, and previous works do not compare EFS with meta-analysis. So, regarding our methodology, Our input data are gene expression matrix obtained from microarray platform. These matrices, they show the expression values of all human genes across tumor and non-tumor sample, and they are especially important in cancer studies to identify patterns of gene expression associated to cancer. So we first collected pre-processed data from GEO, which is a public database of gene expression and other types of genomics data. We got 7 training data sets, all of them related to breast cancer, but they were not filtered for particular molecular subtypes and cancer stage. All of them had certain degree of class imbalance. And we also obtained 6 data sets, independent ones, for testing our models. All training data sets contain at least 10 samples per class. So our EFS design starts for each data set dividing the data into training and validation. The training portion goes to Bootstrap, where we generate the data samples. Each of them goes to analysis bias mode to correct for class imbalance, and it's analyzed by a Bayes selector, which is a feature selection algorithm to obtain a ranking of features relevance for the classification task. These rankings can be compared for stability with the well-known Kansheva index, and they can also be aggregated. Here we use the mean aggregation to obtain a local ranking. So this local ranking, based on subsets of top K genes, which are our features, we can train classifiers using the training data sets and then evaluate its performance using the independent validation partition. So we perform this for each of our training data sets. We have 7, and we can also estimate stability among the local rankings obtained by each data set and aggregate these local rankings to obtain a global ranking. This global ranking is the output of our EFS solution. From this global ranking, we obtain the top K features, train a classifier using the training data sets, and then the model generated with this data can be assessed with test data sets for predictive performance in the classification task. Our baseline method is a random effect model, which is widely used in the transcriptome analysis. It's very similar. Each data set has a ranking produced in terms of differential expression of its genes provided by log-fold change and p-value, and the statistical combination of all these p-values generate a global ranking. And the same procedure can be then applied, subsetting the top K features, training a classifier, and evaluating the model with the same set of test data sets. So in our experiment, we vary the threshold for the top K genes, the number of pegs from the Bootstrap process. We use 5 Bayes selectors widely used in this domain, and 4 classifiers, 4 distinct algorithms to train our classifiers. Performance evaluation was based on F1 score, and the stability was analyzed with Kansheva index, which is widely used. And in summary, when we have values above 0.5, it indicates a high stability among several rankings. So I'll briefly talk about our results. I started looking at global stability in a summary for all the experiments. So here we are showing the stability for the subset of genes selected. First, we can see that stability increased with the size of subset selected genes, and also that the values are limited to 0.3, which indicate moderate stability. We hypothesize that this may be related to heterogeneity among different data sets related to cancer. And also the top 5 genes, they showed somehow a value comparable to the top 20, which may suggest that more agreement among rankings in the top genes is occurring among different methods. We did not observe any impact on number of pegs, but we noted that variance was by far the best feature selection method in this particular case that we are investigating. So now I'm showing the local stabilities for all the experiments. These local stabilities are related to each data set, and here we have a distinct scenario. We can show that we can see that local stabilities are notably higher than the global one, which may corroborate our hypothesis about data heterogeneity, and also that in some data sets, for instance, this one it's larger than the others. So this, not by coincidence, it's our largest data set. Also, variance was the most stable method across all the data sets. The second point was analyzing the predictive performance of classifiers trained with the top 20 genes. So we chose top 20 genes provided by the variance feature selector method, which was the most stable. F1 score in general is very high, considering that this is a challenging task. And we could see that it varies more with the data set. These are the test data sets, independent ones, than with the classifier itself. Each data set has patients with particular clinical characteristics that may generate this variance. We observed that SVM in general was the best method according to F1 score, which is the harmonic mean between precision and recall. But KNN in particular was very good for recall, which is recovering the positive class correctly. Our positive class are tumor samples. When we compare our EFS approach with meta-analysis, we had very good encouraging results, because EFS was better than meta-analysis in 4 out of the 6 data sets according to F1 score, and in some of them with a large difference, a margin of difference among both of them. But what was very curious in this experiment is that when we analyzed the top 20 genes for both methods, we observed that there was just one gene overlap among the two. So this gene is known to be highly expressed in breast cancer, and some work suggests that it may be involved in early tumor progression, but this is something that we still need to look more carefully. We know that there is a lot of correlation among genes, so considering correlation may be a future direction of this work. So concluding this presentation, we propose an EFS approach that achieved very high local stabilities. I mean, for each data set, stability was very high, which is very interesting for biomarkers because we want them to be reproducible among distinct populations. But global stabilities were moderate, varying between 0 and 0.3 in a -1 to 1 scale of Koncheva index. So data sets heterogeneity should be investigated and addressed in future works. Here, we consider breast cancer in general. We do not consider any particular subtypes of breast cancer. Our approach presented better performance in 4 out of the 6 test data sets compared to the state-of-the-art method for combining transcriptomic data. And we observed low overlap among the top 20 genes. So this gives us new questions to be investigated in future works. Do these genes have distinct or even complementary functional roles in the pathogenesis of cancer? So we need further investigation to analyze the biological pathways, see how they connect to the development of cancer or progression of cancer, and also elaborate on how we could possibly joint leverage their findings from EFS and meta-analysis in future studies. So this is still an ongoing work. I would like to conclude thanking the financial support from our Brazilian agents, CAPS and CNPq, and I'll be happy to address any questions. Thank you.
Thank you to you for the nice presentation. Are there any questions, thoughts? Okay. What are your expectations for the application of your method in the real scenarios?
I think that the great advantage would be to point subset of genes that they could use for a diagnostic tool. Instead of using, for instance, 20,000 genes, which is currently used at a microarray, we could do chips that measure the expression of, let's say, 20 or 50 genes that could be cheaper and also provide high accuracy on diagnosis. So this would be the final application that we intend.
Okay. Thank you so much. Thank you so much.
Thank you.
Thank you to the other participants, and we welcome you to the rest of the conference. We'll see you later in the afternoon for the open ceremony at 15 past 2.
Bye.